Yo, what's up, everyone? This is LeetCode 236, lowest common ancestor of a binary tree. We've done this problem in Python, as you can see. We're going to do it in C++ now. So this problem is very similar to LeetCode 235. The only difference is the trees are structured differently because this is a binary tree in this problem. 235 is a binary search tree. So it's just like the ordering of the tree is different. I recommend doing this problem first. It's really not too hard, and it helps you understand 236 a little bit better. But yeah, so we have a binary tree, right? So it's unsorted. So it's not that easy to just decide whether we go left or right in a particular moment. So we basically have to do everything and like recursively handle everything, right? Because we don't know where P or Q are exactly in the tree. Like we don't have like a general idea because the tree is unsorted. Or unordered, I should say. So again, this problem, just like 235, right? We have an LCA we have to find between P and of P and Q, right? Maybe I shouldn't say it's so matter of fact because maybe you haven't done 235, but I mean, again, I do recommend you do it 235 first, rather before you do LeetCode 236. But right, a lowest common ancestor is defined between two nodes P and Q, such as the lowest node in T that has both P and Q as descendants, and a node is allowed to be a descendant of itself. Okay. Now, I want to make something clear, which is the constraints, right? Pay attention that P and Q will always exist in the tree, so they're guaranteed to be in our tree. And all node values are unique, okay? So, how are we going to handle this, given that this tree is unordered, right? We have to find the LCA. Well, we're going to have to do recursion, right? So we're going to have to handle left subtrees, right subtrees, all that jazz, right? Much like recursive tree problems that we've done in the past, if you've been following me on the Grind 75 journey, right? We've done similar approaches to tree problems where we just have to recurse and find something, right? So the way we're going to do this is we're going to start at the root node, which is because that's what we're given, and we have P and Q, right? So we're going to go left, and we're going to see if we can find P or Q, right? So we found P, right? So P basically gets marked as 5, and we go up. Then we go right. Oh, guess what? We found Q. Okay, this gets marked as found, and we go up. Now when we're up here, did we find something in the left subtree and the right subtree? Yes, we did. So that means that this is the LCA, so we'd return 3, right? Now here, this is slightly a little bit more complicated, but not too complicated, right? So we start at the root node, which is 3. We go left. Okay, do we find P or Q? Yes, we found P, which is 5. So this is, we mark this as the left, right? And then we go right, so we go back up, and then we go in the right subtree, see if we can find P or Q, right? We didn't find anything. Let's keep recursing. We go here, nothing. Left, right, empty nodes, nothing. Go up, go here, nothing. Go left, go right, nothing. So we go all the way back up, and when we get to this 3 again, we basically go, hey, we found something on the left subtree, right? This P here, but not anything here, right? So we only found one node, which is kind of weird. So what does that mean? That means that the other node must exist in this subtree somewhere, right? Why is that the case? Because remember, they both have to exist in the tree somewhere. So when we're up here and we return, if we didn't find anything, the other node somewhere over here, it means that the other node is below this somewhere, right? But it doesn't matter ultimately, because if P is below Q, then P is the LCA, right? Because, and remember, a node is allowed to be a descendant of itself. So even though 5 is equal to P, 5 is the LCA, right? Because of this here, okay? That's why I'm saying do LeetCode 235 first. It makes this problem a little bit easier to understand. But yeah, shouldn't be too hard. Am I missing something? Let me think. But yeah, so we found P here. We didn't find Q anywhere. But that means that Q has to be somewhere below this, but ultimately it doesn't matter because we're returning this in that case, right? Which is what we do. We return 5. Okay. So I'll just go through this illustration quickly. I'll just re-explain basically what we're doing, but I can actually draw it now, right? So we have P as 5, Q is 1, right? So we're going to go here, so we're going to start here, right? We're going to go into the left subtree. Okay, is this 5 equal to P or Q? Actually, yes, it is equal to P. So the left node gets marked as this. So we go back up. Okay, and now we go right, the right subtree. Okay, well, we found Q, so this gets marked as the right subtree. Okay, so we go up. Now when we're at this 3, left is marked as something, so is the right. So that means we found both nodes. So this has to be the LCA, and that's what we should return, right? 3. Okay, here we have 5 and 4, right? Start at the root node, go left. Okay, 5 is equal to P actually, so this gets marked as the left node. We go right. We never find anything, right? We go here, 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 go up, go here, nothing. Left, nope. Right, nope. We go all the way back up. When we go here, well, is right set to anything? No, actually, it's set to null because we never found P or Q. So that means that we found one node here, but no nodes over here. So that means the other node must exist somewhere over here ultimately, but it doesn't matter because they'll never be the LCA because this will be the LCA. So this is actually what we return. And the condition to return here is basically, okay, if left has something, but right doesn't, return the left. Likewise, let's say this wasn't found, but this was a, I don't know, P or Q. This would be what we return, right? Because right would exist, but left wouldn't. Now, if left and right exist, then the node they descend from is actually the LCA, not right? Because like if we're up here, like how can this be the lowest common ancestor? This is not an ancestor of 1. Likewise, 1 is not an ancestor of 5. 3 is an ancestor of both, right? But here in this example, like if Q is 4, of course, 5 is a descendant of itself, remember? And 4 is a descendant of 5 as well. So that's why, like, when one of them exists in 1 tree above the other, you can return that. But if they're kind of separate, like on different sides, then the LC has to be the node they descend from above, right? And that's why like doing this recursively is really helpful. Okay, so let's go this up. So we're gonna say we're gonna do this recursively. Remember, so we're gonna say if there's nothing on the root, then we can just return null. Just return null. Now if P is if we find P or if we found Q, we can just return the root, right? Because we found them. And then this is where we basically go on the left subtree and the right subtree, right? So we're gonna say left, we're gonna say lowest common ancestor, we're gonna say left P Q. Okay, we're gonna copy this just so we can, just so I don't have to write it. I'm a little bit lazy. We all get a little bit lazy sometimes. So this is gonna be for the right subtree. So we're gonna say right, go here, this, okay. So basically, if we find something, because again, we're recursing on this function, right? So if we are like at our child node or something, and there is no child node, then root would be null, and we would just return null, right? Because we don't care about anything there. Now, if we go left, right, and again, like remember, this is a recursive call on this function, so root is changing, right, depending on what recursive call stack we're on. So don't get too confused by this being named root. So just keep that in mind. Okay. So maybe I should write a little bit more code and then I'll explain. Root. Oops, I didn't mean to type that exclamation point there. And root. Otherwise, if left, return left. Else, right. Not gonna work. I'm missing some syntax here. Don't usually code too much in C++, but I think that should work. Yeah. Okay, I'll explain this really quick. So let's say we're at this 8 and we go left and right, right? The node is going to be null, so we just return null, right? We don't care about that. Now, this here is basically what's important, right? Because like if we're at this 3 and we go, like when we're here and we go left, right? We're recursing to the function again. Okay, root has something, but is it equal to P or Q? Yes, it is. Because let's say we go left, right? This node that we're on, which would be the new root, would be equal to 5, which is actually equal to P, right? So 5 is equal to P, or I should say equals to P. So this is what we return up, right? So when we're at this 3, on the left side, we returned a 5 back up, which is going to be assigned to left, right? And then we go here and we go recurse on the right subtree, right? So we go here. Okay, we found a 1, which is actually equals to Q. So we return this 1. So when we go up to this 3, the left is equal to 5, the right is equal to 1. They're both equal to something, right? So we know that P or Q is on the left, and then P or Q is on the right also. So this is the LCA, the node that we're on, which is 3. So that's why we're returning. Now, likewise, let's say example 2, right? again, remember we go left, we find something and we return. On the right side, we never found anything, right? So if we have something on the left side, we return whatever's on the left because that's the LCA. Otherwise, we return whatever's on the right because that's the LCA. Because we would never return the current node that we're on because, we return up here if P and Q both exist on the left and the right subtree, we return the current node that we're on up here, right? Which is why down here is basically the other edge case, which is like, okay, P and Q exist on the left subtree, so let's just, if we found P and Q on the left, just return wherever that occurs first, okay? So yeah, again, I really recommend doing 235, LeetCode 235. Like, I'm serious, it will help a lot. This problem isn't too hard, I don't think, but just like doing a binary search tree, using a binary search tree, and having like an ordered tree makes this problem a lot easier to understand, in my opinion. So do that one first. It shouldn't take you too long, actually. It's simpler than this one, and I don't think this problem too crazy. I think if you're doing this one before 235 though, it is a little bit more complicated to wrap your head around. But yeah, just knock 235 out really quick, and this one should be pretty easy. I think they kind of build off of each other. So anyways, I hope this helped, and I'll see you in the next one. Peace out.